Good evening, ladies and gentlemen, distinguished guests, and esteemed colleagues. It is my honor to welcome you all to Professor G.K. Trivedi Annual Award Lecture 2025. Today, we gather to celebrate the legacy of an exceptional individual who has left an indelible mark. Professor Girish K. Trivedi is a name synonymous with excellence in teaching and research. During his illustrious tenure from 1966 to 2002, he played a pivotal role in shaping the Department of Chemistry into the esteemed entity that it is today. As we celebrate his contributions, we also recognize the impact he has had on generations of students and colleagues. His dedication, passion, and leadership have inspired countless individuals to strive for excellence. With that, it is my pleasure to invite the head of the chemistry, Professor Ruchi Anand, to present a bouquet to Professor G.K. Trivedi. I would now request ma'am to take the stage and share a few words with us.
It's okay, I think I got it. Good afternoon, everyone. It's a pleasure to have this fourth Professor G.K. Trivedi Award Lecture. And before we begin, I would like to say that this lecture series was actually instituted by the students, and many of them I see are here. Dr. Lakshmi is here, and as I hear it from the students itself, is that on the during COVID, at the 80th birthday celebration, and what I gathered was Professor Trivedi, you are a very, very popular teacher, and they love you so much that they used to meet every birthday, I guess, and have either a lecture or some kind of a gathering, and they decided that they will come together, and then they instituted this lecture. And this lecture has seen very, very distinguished speakers. We have had Professor Eric Carrera a couple of years back. Then we had Professor Brian Stoltz from Caltech also give a talk. And now we are very lucky to have Professor Peter Seeberger to also grace this equation. So thank you for coming. And thank you to all the students and Professor Trivedi for being here. We are really, really grateful that you are able to come today and be a part of this event. And with that, I will actually let the lecture begin, and I will ask the Professor Swarn Kulkarni to introduce the speaker.
It is my pleasure to invite Professor Suvarnas Kulkarni to chair the session. Thank you.
Thank you, Ratika. Thank you, Ruchi. Yeah, it's indeed really a huge honor for me to get the opportunity to introduce today's G.K. Trivedi Award. So today we have very distinguished visitor with us, Professor Peter H. Seeberger, for giving this award lecture. Peter, many of us, we know him well, and he has been a frequent visitor. We are very fortunate to have him. This is probably the 5th time he's visiting us. He studied chemistry at the university in Nuremberg in Germany, and he completed a PhD in biochemistry in Boulder, USA, working with Professor Carothers. After that, he moved to Sloan Kettering Cancer Center Research at New York and worked with Professor Samuel Danishevsky for his postdoc. And after that, he started his independent career at MIT, where he got the full tenure and became the Furmanek Associate Professor at Chemistry. And at that time, they were really publishing great papers, and we used to read those papers, fascinated by his chemistry of glycosyl phosphate at that time. Then he was invited to join ETH, where he moved subsequently and worked for the next 6 years. And after his tenure at ETH, he assumed the position as director at the Max Planck Institute of Collides and Interface in Potsdam, and also as a professor at the Free University of Berlin in 2009. And in addition, he serves as honorary professor at the University of Potsdam. Since 2021, he is a vice president of the German Research Foundation, DFG, which is the main funding body in Germany. He is also a member of Senate. He is a member of the governing body of the Max Planck Society and the Veterinary University, Hanover. Professor Seeberger's research on chemistry and biology of carbohydrate vaccine development, and continuous flow synthesis of drug substances. It spans a broad range of topics from engineering to immunology, and he has published, huge amount of papers. You can see over 600 peer-reviewed journal articles, many of which are in top-flight journals like Nature, Science, JACS. And he has published more than 4 books and more than 50 patents and over 200 published abstracts. And he has given close to 1,000 invited lectures. This work was recognized with more than 40 international awards in the US, and I'll read some of those. I don't want to cut short the introduction due to the occasion and for the interest of students. So some of these awards from US, for example, Arthur C. Cope Young Scholar Award, Horace B. Isbell Award, Claude S. Hudson Award from American Chemical Society. Then from Germany, also he has received, for example, 2017 Stifter Verband Science Prize, Korber Prize for European Sciences. He also received Hovinga Medal from Holland. He received honorary lifetime member of Israel Chemical Society from Israel. Also received Yoshimasa Hirata Gold Medal from Japan, and the 100 most important Swiss from Switzerland, and honorary doctoral degree from UCT of the Czech Republic. He also received the most prestigious Whistler Award in 2012 from International Carbohydrate Society. In 2013, he was elected to the Berlin Brandenburg Academy of Sciences. Peter Seeberger served the scientific community in many functions. He greatly supports the idea of open access publishing. He is the editor-in-chief of the Beilstein Journal of Organic Chemistry and serves as the editorial advisory board member of several other journals. And through his work in the area of neglected diseases, Peter Seeberger has become involved in philanthropic causes. He is a co-founder of the TESFA IIG, Hope for Africa Foundation in Ethiopia, that aims at improving healthcare in Ethiopia. It recently helped to build a bednet factory and establish an IT training center as well. And we were talking, more than 75 of his co-workers, postdocs, students have got academic positions around the world. And his research has given rise to several companies in USA, Switzerland, and Germany. I think, to me, 2 of his very seminal contributions, which deserves Nobel Prize. One, he thought of this idea of carbohydrate-based vaccines for infectious diseases, where he has made remarkable advances. And second, he has developed the automated oligosaccharide synthesizer. So we are very, very honored to have him. And without much ado, I would request Professor Seeberger to give his talk. Thank you.
Well, dear colleagues, thank you very much for the invitation to come back to IIT Bombay. It's always a tremendous honor to be invited, and this time particularly, of course, it is a humongous honor giving a lecture named after the real giants who built this place. And I think building a place of that prominence, that is really something very few people can say. So it's really an honor to be here and give this lecture named after you. And thanks very much for all the colleagues make it possible for me to come here. Now, after the introduction given by Professor Kulkarni, it's a little difficult trying to live up to that. It'll be hard. So I will talk about just a few relatively simple ideas. And for the students, maybe you realize that it just took a couple of simple ideas And if you then continue working on those ideas and be persistent for a long time, then sometimes even some applications can come up. And the first simple idea I'd like to talk about is if you take a look at chemical reactions, and I know many of you are really hardcore card-carrying organic chemists, and many of you will say, well, putting a phosphate diester in place, that is really not that difficult. Huh? It's not even a stereogenic center. All I got to do is just couple it. So how hard can that be? And people in the 50s, of course, worked on that. But my PhD advisor, Prof. Carruthers, worked at trying to understand this reaction. And eventually he was able to automate this reaction. And today, DNA is made in autonomously working facilities where no human actually interferes anymore. And today it's at a point where most of my students believe that DNA is made by DHL, because you send an email and 2 days later a DHL package shows up in the office with a DNA. It's actually made by other places. Anyway, so once you can do that, you can actually commercialize these reactions. And my PhD advisor started a company called Amgen. You may have heard of it before, but he became a multi-billionaire because of that. So there are many applications afterwards, sequencing, many other things. I would even go as far to say that siRNA and other things are only possible because somebody actually understood this reaction. And I think the whole life I spent, I try to think about, can I understand one reaction? I'll show my favorite reaction. I know that your favorite reaction is most likely different from what I do. So anything I show you today, just take it with a grain of salt and say, well, I don't really care about glycosylation, but maybe I could do something similar for your favorite reaction and understand that I can make a difference. So what we'll show today is carbohydrates. And the synthetic chemists amongst you will say, carbohydrates, really, really boring. Huh? I mean, always the same building blocks, it's just sort of monosaccharide. Yes, okay, it is branched, unlike DNA, so we have to make sure we get retroselectivity. Okay, and yes, every glycosidic linkage we install is a new stereogenic center, which means you have to exercise stereo control. And that makes it more difficult than DNA chemistry and peptide chemistry. And then we have things like modifications such as phosphate or sulfate. And of course, many, many carbohydrates, if not most, are actually conjugated to proteins. So that is the reason when I started to think about what I would do for my own academic research, I thought, okay, some guy automated DNA chemistry, my PhD advisor. Merrifield automated peptide chemistry. I'm a simple kind of guy. I thought I'll do carbohydrates. And most people said, well, that's going to fail because that's too hard. Nobody can automate that. Luckily, I didn't listen to them. But the chemistry of carbohydrates is by no standard new. This is a paper by Emil Fischer. You may have heard of him. So my predecessor at university. In 1893, he talked about, in German, the synthesis of glycosides. Now, if you read the textbooks, what you see is that a leaving group takes off from a glycan, a glycosyl cation is formed, but is attacked by a nucleophile from a top or bottom, giving rise to two different stereoisomers of glycosides. Now, the interesting thing was that I used to also teach that at a university, but the fact was nobody ever saw that intermediate. And in 2018, we published a paper finally. We actually published the first observation of a glycosyl cation with direct methods. Took only 100 and some years to figure out what's going on in between. So, all right, that was one thing. The second thing is, and I apologize for the somewhat complicated picture here, glycosylation is seemingly simple. It's a glycosylating agent, and it's a nucleophile, an alcohol. So how hard can that be? Well, the problem is that there are many factors that play a role. The nucleophile, nucleophilicity plays a role, steric hindrance plays a role, electrophile plays a role, temperature, activator, solvent, and basically you can have a range of different mechanisms coming from SN1 to SN2 and anything in between. And this is what's given carbohydrate chemistry a bad name, because it's almost impossible to predict what's going to happen. That means for our PhD students and undergraduates, lots and lots of optimization work trying to figure out exactly what's going on. So about 24 years ago at MIT, I decided that maybe I would like to replace all my PhD students with machines. Why? Because even a good student can maybe do 4 new reactions a day, maybe. And when they complain because they want to take weekends off and things, the machines don't complain.
And so I'm joking partially. And so we thought, okay, maybe we could think about flow chemistry, and at that time it was really novel, flow chemistry making matters easier. I should say we started a project in 2001, and the first really important paper in this area took us only 17 years to get to. The idea is rather simple. We will have a small chip, 60 microliters. We put a donor, we acceptor, we activator, we mix it, retain it, quench it, HPLC behind the whole thing, and the result of the HPLC goes back into the scientific experiment software, trying to run this in cycles. And that actually starts to work. That means we have high precision, high reproducibility, small volumes, and we can interrogate 13 different variables. Now, the details of this slide are completely irrelevant. However, if you're interested, you can read the paper. But what is interesting for us was the fact that we could actually begin to predict the outcome of glycosylations and their temperature and other reliabilities based on machine learning. And that was a paper published again 4 years ago. This is one of the early papers on using machine learning, trying to predict things. And the goal for me is to make myself, maybe other professors in carbohydrate chemistry, obsolete, such that a student in their first year of a research lab could go to an expert system. Expert system says, take this building block and that building block and this temperature, and reaction will work the first time. That is really the goal. And I think we're getting very, very close to that today. Now, when you take a look at what we did at that time, what you will see is, yes, the glycosylating agent plays a role, the nucleophile plays a role, the activator, and the solvent. And we will all say, well, we knew all that beforehand, so what's the big deal? Well, that was not all. We also need to understand the reaction a little bit better, because what we do know is that there's a leaving group that gets activated. Then there's going to be a bond breaking process, freeing up the cation, and then that can decompose, or it can lead to productive glycosylation over here. So we tried to actually look at this in more detail. Now, I don't know how a Kulkarni group does their reactions, but what happens in our lab oftentimes is that we start at a low temperature, then we ramp up over time, and then we go to another temperature. Because the problem is every building block will be activated at a different temperature, and we don't know the temperature, which means we have to go to really long times. If we would know the exact temperature, we could just do it, and 10 seconds later, everything is over. So what you then have is you have a bunch of different building blocks with different protecting groups. Don't worry about the details, totally unimportant. But basically what you then see is that some building blocks will be super active, and they'll react at really low temperature, some at minus 20 and some at minus 10. If you go too low, nothing happens. If you go too high, hell breaks loose and everything happens. So you have to be exactly at the right temperature. And this is where my students spend most of their time trying to find the right temperature. And that is really a waste of time for my students, because they're smart. They shouldn't be in the lab just checking temperatures. So what we did, and again, the details are not very important, we want to understand what is that temperature where things actually going to take place. So you can take the NMRs of that, and here what you see is the temperature below minus 8, nothing happens. Between minus 8 and minus 2, things happen, and above minus 2, things go bad quickly. So an undergrad student actually looked at that, because my PhD students did not want to do that work. The undergrad spent 6 months in the lab, and then he got to publish an angewandte paper. And the PhD students were jealous, because they didn't want to do that work, because they thought this was just a waste of their time, which turned out not to be the case. So another thing we looked at, and that was very surprising to us, that glycosylations are very dependent on water. Now, if water gets in there, things go wild and bad. That's not what you want. But interestingly, what we found is, depending on the amount of water, 1 ppm or 23 ppm, so quite low, the activation temperature actually changes. And that is relevant for the following reasons. Imagine I do my reaction in Potsdam in winter when it's cold and dry, and then Soban Kulkarni's lab tries to do it in Mumbai where it's warm and humid. Then you're going to have a different activation temperature. So I publish, oh, my reaction works at minus 5, and then Soban realizes that his actually works at minus 20. That becomes a real problem, because those reactions are very, very sensitive. So we have to understand and report reactions properly. So what we need to do is, we need to get a much better understanding for each coupling. And so far, I've only focused on the building blocks. So the building blocks are important, because some of them are disarmed, if you have electron withdrawing groups, armed, if you are having electron pushing groups, but it also depends on the acceptor, on the nucleophile. So you have both partners. And so far in that undivided paper, all we showed is that the donor is important. But now we want to also show you, well, it's also the acceptor. And Mei Hui Lin, a PhD student from Taiwan, was charged with a thankless task of trying to look at 144 combinations. Now, just to make matters worse, it's not 144 combinations. It's 144 combinations at 10 different temperatures. Now, I don't know which one of the students wants to do that. This is not fun. You got to do the same stupid reaction over and over and over again. Every time you got to determine the yield and the selectivity and everything else. So that is not that exciting. So she was also not excited, but she had no choice because I'm her boss. And she did really a fantastic job. She is really, really good. And what she did together with Jacob Wolf, another PhD student in the lab, they basically built an instrument where we have the building blocks, the acceptors, the activator. We can go to very low temperatures. We have an LC ELSD MS behind that. And we can then feed a database using this. Now, this is the instrument they built, and this is the overall instrument. Now, this is the new version. This is as of yet unpublished. We'll submit it very soon now. But basically, what we have here is the automation and control over here, delivery, injection valve, and the biggest part here is actually the ALC ELSD MS. Now, that instrument works 24/7, and that is what they actually got to work. So what we got to do now is we're going to do a matrix of the different building blocks at the different temperatures. And what we're going to get out of this are things that look like this. We'll have a pop quiz afterwards explaining the details. No, what I'm trying to say is we can get the data points now. Every 20 minutes we get a data point. So in 1 week, these two students produced more results than my entire department of 100 people produced basically a year previously. This now works and can be applied to any building block. And the reason I show this to you is not because you could care about the carbohydrate building blocks, I understand that. But imagine we could do the glycosylations, you could do cross-coupling reactions, you can do any reaction you like on such a system, and that means you can get reliable, reproducible data that can afterwards guide your discovery process without you having to spend 24/7 in the lab. And that is really what we want. We did that and we got heat maps. So if we understand the reaction, we can then think about automating the reaction. Of course, we did it a long time ago. Sovan briefly pointed out, we discovered it a long time ago. The principle is quite simple. You have a polymeric support with a hydroxyl group. You're going to do an acidic wash. You're going to couple the building block to connect the sugar to the solid support. You do capping. You then deprotect the hydroxyl group, in this case, to get ready for the next glycosylation, or you can also do modifications. And what you see down here now is it took us 100 minutes to incorporate one building block. Now, most people say, well, 100 minutes, I know DNA, how long does it take? 3 minutes or something, right? Peptides, 2-3 minutes. Why is it so slow? Most who know me, I'm impatient. I said to my students, why is it so slow? Well, when I was a postdoc, it took 3 of us 2 years to make a pentasaccharide. Now one of my students can incorporate actually one building block today in about 45 minutes. This is 2 years old. 45 minutes is what we take today. I think we will be able to get this down to 15 minutes for each incorporation. So that gets faster. Now, eventually you can take the glycan off, you can characterize it, and of course, as you have a new technology, there's a race who has got the biggest carbohydrate. And in 2001, we had 9 MERS, and eventually we got up to over 150 MERS, and the Chinese have used the technology now to make 1,000 MERS. So the sky's the limit. You can make really long sequences. But I'd like to briefly show the work of Auragan Joseph. He got his PhD in Taiwan, and he made 150 MER in my lab, and I've shown that previously here. And then he did something really crazy. Joseph said, well, Peter, I'm going to make all of these structures. And I said, right, that's not going to happen, okay? Because in Danishevsky's lab, I made this one, 3 people, 2 years. I said, okay, I believe you can make some of it, but long story short, he's made them all now, by himself. He learned the rules how to do this, and we could teach any one of you to make the structures within less than a week. Make one structure, but the teaching will take less than a week. So that has really opened unbelievable possibilities. We'll submit his paper now next month, hopefully to a good journal. We'll see if they take it or not, but that's the hope. And of course, then you can go crazy. You can look at what people have done in peptide chemistry. And Manuel Ricardo Garcia, originally from Cuba, but he said, okay, let me make staple peptides, where I put staples in the backbone over here. So I put an olefin in there, I do Grubbs cross metathesis, I put that in here, and you have a helical carbohydrate. Okay, Meyer, what he said is, look, let me make saponins. If you like Ayurveda, that includes lots of saponins, like all traditional medicines, okay? Or you like cyclodextrins. He said, I can maybe make those structures. And what he did is, and this is just published a few weeks ago now, this paper down here, he basically constructs the carbohydrate on the solid phase and then starts building in this direction, or you can actually cyclize on the solid support, and that's going to be submitted very soon as well. Now, the technology was developed in our lab. We didn't just develop it, we also then commercialized it. Some of my students started a company called GlycUniverse. The first instrument, the Glyconeer 2.1, was super expensive. We sold quite a few of those, and then we realized it has to be smaller, it has to be faster, and the new Glyconeer 3.1, that instrument is 4 times faster, 4 times smaller, takes 4 times less energy, and actually was also slightly less expensive. When does your iPhone ever get cheaper, okay? And if you want to see it, go to Kulkarni lab. We are the first one on the Indian subcontinent and have this Glyconeer 3.1 right here in the lab. Okay, so my lab has worked on all the carbohydrates on the surface of the ocean, but then a marine biologist, one of my colleagues at Max Planck, came up and said, Peter, you know that for every kilo of carbohydrates on the surface of the Earth, there's 1 kilo of carbohydrates below in the ocean? I said, no. Why should I care? He goes, well, actually, the following thing is true. We know that there are 50 gigatons of carbon incorporated every year in algae and glycans. They are sequestered, and eventually bacteria eat them, and CO2 comes out again. This entire thing does not enter into our climate models. Now, with global warming, if the algae and algae fix more glycans, that would be good, because more CO2 will be fixed. If bacteria become a little more crazy, they may actually put more CO2 out. So it would be just nice to know what the hell is going on. And the fact is, we know very little. So a few years ago, we said, okay, let's have a look, because we know there are glycans which are important, again, for energy storage, materials like animal shells, and for medical purposes. And the structures are pretty amazing, and there are bacteria that are completely specialized. They will only eat one particular kind of carbohydrate. And they all live together as large communities. So I believe that if you take a look at the ocean, we will find enzymes that make carbohydrates and break and modify carbohydrates, which we have never seen before. It will give us an amazing possibility to actually understand what's going on. So today my lab is really involved in trying to synthesize all these structures, because what we like to understand is how they're made. And this is where I, as a chemist, always get really frustrated, because you talk to biologists. The biologists will tell me, oh, Peter, we work on fucoidin. So I thought, what's fucoidin, right? Oh, that's fucose in there. Right. All right, this is 1,3-alpha, that's fucoidin, and 1,4-alpha is also fucoidin, and 4-sulfate is fucoidin, and 2-sulfate is also fucoidin. So what they say is, oh, fucoidin does this, and fucoidin does that. Of course, because you basically have everything under the kitchen sink that you have there, and then you're trying to correlate biological activity with structure. So you cannot correlate that, because basically it's a total mess. And this is what we like to solve, and as chemists we can do that, because if we can make the structures, this is what we did, published last year, and I have many students now who basically working on these carbohydrates, and the idea is to make probes. This is just one example, where you can see a simple oligomonoside with thread probes on either side. You have an enzyme that hydrolyzes the oligomanos, and you can then do a relatively simple enzyme assay. Again, none of this stuff is particularly creative. People have done this with peptides, with DNA. We happen to do it with carbohydrates. The only difference is we can actually make the probes, and that's where we can do it. And that's shown one more time for another example, but I think you get the idea. You can make samples and you can use them. And here we begin to do now is we can actually begin to image microbial communities. And that paper is in a big journal right now for review, because all of a sudden these people actually have tools to look at the things they're interested in. I'm just a simple tool maker. So for a simple tool maker, it would be nice if you could not just make carbohydrates. It would be really nice if you could combine carbohydrate chemistry and peptide chemistry. So how hard is that, right? I mean, people have peptide synthesizer. I got one, actually multiple ones. And so my student said, let's just take that machine and let's make a glycopeptide. Don't even think about it. My students ruined the machine. 90,000 euros down the drain, okay? I was really mad with myself because I told them you can do it, stupid. Don't do it yourself. And finally what we did is actually we took the one that you have here, the glyconeer, that's this part here, and we expanded the glyconeer to make glycopeptides. This just shows you the expansion here. We can put 22 dedicated amino acid positions, 2 actual activators, and it's a completely isolated system next to the normal glyconeer. And there's a IIT Bombay connection in this particular case that is yet unpublished. This is Kapila Pradhan. Sorry, the best picture of her, but some of you may know her. What she did now is here, she did an automated synthesis of O-glycopeptides, and those who know this, they are the so-called O-glycans. There are actually 8 different cores, and she synthesized all of them by automated synthesis. Right now, we are combining with N-glycosynthesis, and we are trying to get actually a synthesis of EPO by complete automation. So that's what we're working on right now. Of course, you cannot just make natural combinations, you can also make unnatural combinations, as the one shown here. So what we can do here is, for example, we can make a lipid, a T-cell engager peptide, and a carbohydrate in such a way we can take a liposome and stick them in there and have then the glycan exposed on the outside. You can imagine this is very useful for trying to make vaccines. Okay, now I told you we can make structures. The question is, what do carbohydrates actually look like? And if I would ask you the same question about DNA, you would all say, well, of course, polynucleotides from helices and polypeptides from helices and sheets, and we can make DNA origami and all this other stuff. And carbohydrates, they don't fold. That's nonsense, okay? Some carbohydrates don't fold, and some carbohydrates do fold. If they would not do that, the trees outside would be lying flat and not standing up, okay? So that is very clear. So the question is, maybe we can actually look at that. The problem was we had really no good technologies trying to do that, and so we combined our forces together with Max Planck for solid state research some years ago. We used electron spray, put it from a quadrifold mass filter, time-of-flight mass spectrometer, landed on a copper surface, flatten it out, and then do scanning tunneling microscopy. And what we then got was the first picture of a single carbohydrate molecule. This is why I got in the sort of a famous journal, because we could do that. The interesting thing was that we could actually now for the first time look at things which were somewhat unusual. What I show you here, for example, is a cyclic carbohydrate, but it turns out it is not cyclodextrin, as some of you may know, but actually it's what's a linear version of cyclodextrin with one bond from here to here missing. In the gas phase, the cyclic structure is the lowest energy structure, but then you actually hit this with the tip of the STM, you get this linear structure. Is that biologically important? No, not at all. The only thing it shows you, you can actually start to see structures. If you pay attention, we'll say, Peter, but structures mainly in the gas phase. Correct? Now that's as good as we can do right now. We would love to also do this otherwise. All right, so if we can take a look at structure, maybe we can start to actually build structures from first principles. And people have done that in the case of peptides. You can have parallel strands or anti-parallel strands. You can take a turn unit, and all that is known. So we said, okay, maybe we can do the same thing with carbohydrates. We take a blood group, Lewis X, as a turn unit. We take cellulose as a strand. And we combine those two things together. And what we can then get is, for example, this monosaccharide. Now, realize we don't even talk about a synthesis anymore, because the synthesis is done by one student in one day. We talk about how can we construct it, how can we design it, how can we use it. And I have to thank my friend Jesus Jimenez Barbero and his wife to actually do the NMR spectroscopy, because that's a little more involved than usual. And what you find then is that there are quite unusual H bonds, and you can actually begin to form carbohydrate hairpins. Now, Martina Del Bianco, who is an associate professor in my department, she was my postdoc, eventually built this, and now she's building up huge structures based on carbohydrate foldimers. And I think what we see in DNA and in carbohydrates, we'll also see now in the area of carbohydrates going forward. All right, so let's leave material science and let's go to real life. Fact is, we all will most likely die. The question is, how are we going to die? And today, there are multiple choices here, cancer being one of the more prevalent ones. Unfortunately, in 2050, it seems like majority of those of us who are still around at that time may die from bacterial infections of bugs that are resistant to antibiotics. And that is very, very concerning. And I know there's very nice work going on in this department over here. Our approach relies on carbohydrates because carbohydrates happen to hang around bacteria as form of a capsule, the so-called CPS, or capsular polysaccharides. Now, this is the outside of a human cell. The black stuff in here, it's called the glycocalyx. And if the mammalian cell would be a donut, it would be a glazed donut. Nice, but boring. Cancer cells are different from regular cells. That is important, because that means if I can distinguish the carbohydrate code of a cancer cell, I have a way to recognize the cancer, and I may have a way of treating the cancer. And even easier in the case of bacteria, because bacteria perverted, they got all sorts of carbohydrates, and they're easy to recognize. And that's why we focused first on the bacterial surface. So there are three things in this lecture that I'd like to very briefly get across to you. The first is we can create antibodies against these cell surfaces, passive immunization. We can do active vaccination, that would be vaccines. But also another question I have for you. Us as humans, we consist of more bacterial cells than mammalian cells. So how does our body interact with the glycans in our body? I will show you that autoimmune diseases actually are based on some of this. So many of you in this audience, anyone born about after 1995 in India, will be vaccinated with a carbohydrate-based vaccine. And those of you over 65 most likely have been or should be vaccinated with a vaccine against pneumococci. How are they made? Well, today we culture bacteria, we ferment them, we grind them up, we purify them, and then we conjugate them. Sounds really easy, right? Growing, purifying, how hard can that be? The Prevnar vaccine is the most complicated and expensive drug to make. It has 650 SOPs, standard operating procedures, and it's expensive to make. So this is the result. Streptococcus pneumonia sells over 10 billion per year, and these are our two blockbusters. The idea is isolate polysaccharide, isolate carrier, and the carrier is used because humans below the age of 2 and above the age of 65 cannot make a good immune response against carbohydrates. So if you have a carrier, induce an immune response and have a carbohydrate to recognize the pathogens afterwards. So our suggestion was, and that of other people, let's make it very simple. Let's just take chemical building blocks, synthesize the antigens, make semisynthetic conjugates, and make vaccines. And we told people this would not be expensive. The problem was the companies did not believe us. They said, oh, Peter, that's wrong, that's stupid. No, we don't do that. Maybe it's wrong, maybe it's stupid, but actually it turned out it actually works. This is GSK's planned, over 500 million to construct, 100 million doses per year. This is a former postdoc of mine, originally also from India, but got a PhD in the United States. And her technician worked at one of my companies. The two of them, in 2 months, made 1 million doses. Cost per dose, less than 10 cents US. So really, really affordable. So what they did is they actually made a vaccine at Vaxilon, oligosaccharide combined to a carrier protein. Ideally, we won't know attribute anymore, and they looked at Clostridium difficile and Klebsiella pneumonia. I'll show you this in just a second. So how do we go about identifying a vaccine? Well, first of all, we're going to have to synthesize the carbohydrate antigens. Then we're going to have to look for patient samples. If you're lucky in my lab, you may be getting lung fluid. Unlucky, you get stool. Okay, so we have all sorts of things we have to get. Then we do a glycan array experiment trying to understand what is an interesting epitope. We then make the conjugate. Afterwards, we go into animals. I show you here mice, but typically today we work in pigs because for lung diseases, pigs are more similar to humans. The problem is they cost a lot, they eat a lot, and then it becomes complicated. So that's what we have to do. We do the immunology in my lab for all this stuff. Then we will take the sera from the animals. We try to kill bacteria. Then comes the challenge where you have one group of animals which was vaccinated, a second group of animals not vaccinated, and the idea is those vaccinated survive and those not vaccinated will not survive. This is a really frustrating part of that stage because my lab can publish a paper, get a patent, but we have not done anything in humans. And this is why actually we started getting our own companies together. The company I showed you, Vaxilon, got an initial investment of 30 million, and they got to the clinic, and then we sold the company because our people got so interested, they moved forward. I show you now just one example, and this is an old example, but it illustrates the case. Now, Clostridium difficile, you don't want to get it. You don't want to get it in Germany, you don't want to get it in Mumbai. In the best clinical settings, this is not fun, okay? This kills people. And one thing I learned, unfortunately, is that if people that in this area here, but also actually the urban centers of India get this, the chance that people will develop vaccines is much higher because people with money will buy vaccines, people without money will not buy it. And that is a very, very sad truth. And I think we got to think about it as a human society globally, if that's really a great thing, but it is a fact we have to face right now. On the surface of these black bugs, there are 3 different polysaccharides, PS1 through 3. We synthesized them many years ago. We made glycan arrays. We found certain epitopes. Then we conjugated them to a carrier protein. That carrier protein was immunogenic in animals, and mice that were vaccinated actually had a healthy colon compared to animals that were not vaccinated. So this is all preliminary work, and eventually that went then into human clinical trials, and those human clinical trials are right now going on in Germany for that. Of course, once we show this can be done for one bug, you can then go completely crazy and you can try it against a lot of different bugs. And the nice thing for us is the WHO publishes a critical list of pathogens, and we have basically worked on all the ones that you see up here. So that's what's going on. But since I want to make also a connection to IIT Bombay one more time, we also thought about working on fungi. Now, in Germany, in the best clinical setting, we have now young people, like the age of people are sitting in the audience here. They get an infection with a fungus, they go to a hospital, and in 5 to 10 days, they are dead. And there's nothing we can do about it. And that's really, really serious. Now, the reason I'm interested in fungi is because they have carbohydrates on their surface, different ones. And what we did, and I say we, this is Rajat Kumar Singh. He was an undergraduate student in Professor Kalyapan's laboratory, PhD student with me, now at Caltech as a postdoc. And Rajat, he made all these structures a number of years ago. And the reason I can't show anything anymore is because we have already gone now very close to the clinic. These things look really, really good. We're trying to push them into the clinic for fungal infections. So I showed you active vaccination. How about if you just make antibodies? And this is a story the older ones of you may remember in 2001 was 9/11. And afterwards, some idiot thought it was a good idea to send around samples of anthrax bacteria in the United States, killed several people. Now it turns out on anthrax bacteria, there is this particular tetrasaccharide. So a student in my lab today, a chair professor in Freiburg, Daniel Wirtz, he made this compound, and we published it, and then we started making monoclonal antibodies and published that also. And then I got a phone call from the Swiss Defense Forces. They said, Professor Seeberger, we would be interested in developing an antibody as a general detection agent for anthrax. I said, so let me get this straight. Switzerland is a country of 7.5 million people. It's neutral. Why do we need that? They said every time an idiot drops a white powder at a train station in Switzerland, we use a test that costs $50 to check if it's anthrax. So what we did is, long story short, they actually developed this as a test kit, and this test kit is today used by all Western armies to detect anthrax. We did this also for other warfare agents, and most recently, Kapita Pradhan, graduate from here, made one for tularemia, which is also a biowarfare agent along the same lines. The same you can, of course, do also for cancer antigens, and this is what we were interested in. And we use 2 things. We're trying to make antibodies like the ones shown here, which are made by us and mice, but alpacas, llamas, and sharks make what's called a nanobody, which is these very small antibodies. So actually, my department has 5 alpacas outside Berlin at a petting zoo, and we shoot the alpacas up with that. My students hate this because apparently the alpacas were big, but they're really wimpy. So when we take blood from them, they scream so bad, and my students refuse to go there. The animals don't get harmed. They just get injection, and we take the blood. Nothing happens to them. They are with the children on a petting zoo, but the alpacas, apparently, they really scream. So what happened is we got some really interesting antibodies, and a company was formed. We got about 20 million in initial funding for that, and now this is actually being pushed forward for human use together with other platforms. But I like to get to something that affects all of you, and that is your microbiome. I was told at lunch today, Peter, be careful because your German microbiome may have problems with the Indian microbiome. That is may be true, I hope not. But what we do know is that our microbiome actually interacts with a lot of our other organs. And I have to say, I heard about multiple sclerosis before. I didn't really know too much about it. But we were approached by a group at UCSF, University of California, San Francisco, and they said, we believe we may have antibodies in the cerebral spinal fluid that actually recognize carbohydrates and are involved in multiple sclerosis. And what we found were antibodies against this particular monosaccharide in the context of larger structures. Now, I do not believe that these antibodies only recognize, like shown in this case here, S. pneumonia serotype 4. This is a paper we published 5 years ago. We have now continued this. What I can tell you is we find a lot of different antibodies against carbohydrates in multiple sclerosis patients. We are using this now as a diagnostic test in some Switzerland and German hospitals, and we believe there's a clear correlation between antibodies against carbohydrates and autoimmune disease. And that gets me to the last bug I'd like to show you today, and that is P. gingivalis. Now, if you have peritonitis, strong inflammation of your gums, this can be caused by P. gingivalis. 7% of humans have serious issues, and there's strong anecdotal evidence that those people have that. There's correlation to atherosclerosis, rheumatoid arthritis, and possibly also Alzheimer's disease. So about 5 years ago, one of my PhD students started working on some carbohydrates from P. gingivalis. I'm not going to go in details here, but I will say that we've actually identified structures that have clear correlation into atherosclerosis and also Alzheimer's brains. That's interesting because that would mean that if we can prevent an infectious disease, P. gingivitis, we might be able to actually prevent a non-communicable disease, namely autoimmune disease, from occurring. That would be pretty cool. So right now, we are pushing this forward, and the goal would be maybe someday one could make a vaccine against Alzheimer. I'm not saying that's going to happen, but it would be one thing. It would be great if we can push that forward. Last point, Ori Moskowitz in my lab looked into different applications of trying to detect antibodies, and I knew nothing about this, but endometriosis is a disease that afflicts only half the population, females. 10% of females have extremely strong pain because of actually outgrowth from the uterus into other parts of the body. The time in Germany to diagnose endometriosis is 7 years. 7 years. They're told, you're just wimpy, it just hurts a little bit, what's your complaint about? 7 years. Today, we can take 1 drop of blood of a female, and we can detect if it's endometriosis or not. And that's given rise to another company right now. So what I try to tell you in the carbohydrate areas, we have the enabling technology. We developed vaccines, arrays, imaging and sequencing, other things. I showed you all that, but I was told I shouldn't just talk about carbohydrates, and I apologize. We'll go for a few more minutes, okay? And I'll go to something even simpler. I'll go to photochemistry. And photochemistry is really old, and this is Camician in 1912 in Italy. This is in Bologna. They did chemistry on the rooftop of their Tuscan institutes. If you do this in Germany, you could never do any chemistry because sun never shines. But basically, they were fantasizing that in the future, maybe all chemicals will be made by photochemistry. And I'm not so complicated. As I said, we had a simple idea, and the simple idea was to say, okay, this is triplet oxygen, the stuff we breathe. And if you take a sensitizer, a dye, and you take light, you can turn this electron around, and that can relax to become single oxygen. And single oxygen is an extremely good oxidizing agent, a very green oxidizing agent. I thought it would be nice if we could just make that in our lab, because it may be helpful for the pharmaceutical industry. That's all I wanted to do. And what we realized is when you do that, and you're close to the lamp, the reaction is very good. But if you go further away from the lamp, there's a logarithmic decay of photons. And that's a problem. And so we thought, well, it would be really easy if you just take Teflon tubing, wrap it around a lamp, and we know that this is, 5 millimeters or something in diameter, and then the stuff comes out in the end. Now, we published this, and that worked out nicely. I went to a conference to show this, and then somebody came and said, Peter, have you heard of artemisinin? And I'm sure you heard about this. I did not, okay? This is like 2011 or something. And artemisinin is maybe the only good outcome of a Vietnam War. Because during the Vietnam War, the Chinese lost more soldiers to malaria than they did to the bombs and bullets of the Americans combined. So Chairman Mao started a program in the late 60s with the aim of developing a new anti-malarial drug. And what do you do as a student when you get a project? You go to the library and look at the literature. That is what Tu Youyou and her team did. They did not look, however, at Nature or Science or Angewandte. They looked at the old Chinese scrolls, and what they found is that it was written in there that we take leaves from a large brush and you take lukewarm water, you can then treat certain diseases that result in fevers. They tried this with hot water, and it didn't work. Then they tried with lukewarm water, 70 degrees, and it worked. And why is that? Because by the end of the day, as they found out, this is artemisinin that she discovered. She got a Nobel Prize for this. And what it is an endoperoxide. And in hot water, the endoperoxide is not stable. So that is the reason. So today, this is extremely powerful medication. I'm also sure it's made in many companies in India, used by many people, extremely powerful. The sick thing is that still many people die today because the drug is too expensive for them. So what I was asked by companies, they said, well, you know, Gates Foundation gave $53 million in 2012 for Sanofi and for Amyris, a company in the United States. This company, Amyris, makes a yeast production of this molecule, but actually DHAA is the last biosynthetic molecule in the plant. Afterwards, it's no more enzymes. It's the following reaction: single oxygen, acid, triple oxygen gets you artemisinin. None of this was discovered by me. Other people wrote this. I said, Peter, maybe with your flow chemistry method, maybe you could make artemisinin. And we went to the company in the United States, and we said, can you give us this or this material? And I said, Peter, we're happy to give it to you. Please sign that all intellectual property that you're generating belongs to us. I said, sorry guys, sort of German taxpayer money, we can't really do that. So we went to eBay, and we bought 1 kilo of this material from China for $800, okay? So my student put it in the synthesizer, and this is a machine built here, very simple. It used to be a mercury lamp, eventually it was LEDs over here. We take oxygen, we take this waste material, we take, shown here, we take TPP as a sensitizer, we dump it in here, low temperature, we add acid, higher temperature, and out comes about 70% of the drug. That was nice. So I had a meeting with Bill Gates, because he had just dumped 53 million on Sanofi. They built a factory for 25 million with 7 3,500 liter tank reactors. The problem with tank reactor, I told you earlier, that's not so good, right? It would be better to flow. And he said, well, Sieberger, that's wonderful. This is great. We should really fund you. And then they published a call for proposals trying to crack my process. I'm like, why would you do this? Because we have patents on this. We said, look, we're going to give you a patents free of charge if you make the drug cheaper. If you make more money, I'm not giving you patents, right? I want the poor people have really inexpensive drug. That is a goal. Well, so we thought about it, and we thought maybe before these guys are going to crack our process, we got to improve our process and make it better and cheaper. And the most expensive part of our process was actually the sensitizer. It was so expensive that we had to recover it afterwards. We couldn't leave it in the reaction. And we thought about it, and we thought, okay, it's weird because everything to make artemisinin must be in the plant because the plant makes it. So it must be also a sensitizer. And I don't like gardening. And that's maybe the reason why it took us so long. But if you like gardening, then you realize the green stuff is actually chlorophyll. And chlorophyll looks just like this. So the experiment we're now going to do is a green chemistry experiment. True green chemistry. It's actually a green solution, okay? So we take a plant material, we dissolve it in toluene, we add compressed air and acid, and it doesn't get cheaper than that, and out comes artemisinin in the end. So we basically do the same thing the plant does, just faster. And then it took us only about 8 more years. But about 4 months ago, Manos Bio is a company in the United States who makes a precursor biosynthetically, was awarded 32.4 million, and we got 6 million into the company where we started to do that. And we are now scaling this up to make this in the United States at 100-ton quantities for people with malaria. But while we got frustrated about this, because the malaria thing, I thought, stupid, I'm not going to do it. We started looking into the literature, and it turns out that people describe that artemisinin works against everything, including cancer. And I thought, that's wonderful. We have a really cheap cancer drug. Why wouldn't you do that? Well, A, you can't patent it, huh? And B, you have to make it. And if you make it, then people say, why do you give it to poor people? Because now you're using it for people in cancer. So we thought, okay, maybe we can just test it. And what we did is, with our company, we started taking land in Kentucky. If you like Kentucky, maybe horses there, right? And whiskey and tobacco. Tobacco, luckily people don't smoke so much anymore, so the fields are cheap. So we got fields and we started growing and we made 100 tons of this plant material, which is a special seed. The seed is $50,000 per kilo. We start growing the plant, it has 1.8% active ingredient. And we started to do something which sounds completely esoteric. And I'm many things, but I'm not esoteric, okay? And what we did is we started to look in trying to use this in clinical terms. We got an IND, investigational drug application, by the FDA. We went to the Marquis Cancer Center, University of Kentucky, and we looked into ovarian cancer. And for females, ovarian cancer, it's really bad. What happens, they get diagnosed, they get treated, and after 18 months, 87% of females have ovarian cancer again, and then they'll die. So we said, let's try that. Let's try it. And it happened in this phase 1, where we showed that up to 4 cups per day, up to 4 doses per day, were non-toxic. And then something weird happened. This went multiple years. Only 1 woman in the trial died. All the other ones had no recurrence. So the people in the cancer center said, well, see, that's interesting because we've never seen anything like this. And this is cheap, okay? I mean, this is maybe $100, $150 a month or something. How about we do something that's a better measure than die, not die, right? That's not a good measure. What about we do prostate cancer? We have a PSA level, prostate-specific antigen. We can measure a number. And about a year and a half ago now, we began a phase 2 human trial for prostate cancer. And I cannot tell you the details yet, but I can tell you we are very, very excited. So that may give a chance to have a really cheap medication, not to treat cancer, but prevent the recurrence of cancer in those cases. And that brings me to the last 5 slides, I promise, and that's just my new hobby that Solvarn asked me to introduce. During the COVID pandemic, Germany decided that they would have a big grant proposal challenge with a total of 2.5 billion euros, so about 3 billion US dollars, to fund 2 centers, and I was lucky enough to win one of those 2 centers. And I've been charged with trying to build a new institute for 1,000 people. And this is an old sugar factory. I thought for a sugar chemist that's sort of fitting. But it's also, of course, a circular economy. And what we are trying to do is we are trying to totally change the chemical industry. And what we would like to do, and I think is important eventually, is to convert the chemical economy into a circular economy where we start with raw materials, make products, but we can go back. Because today the entire chemical industry is based on fossil resources, oil and gas. And that, from a long term, is not going to be a solution for us. That means we have to develop a completely new chemistry, catalysis, engineering, waste valorization. This will be a huge task. And to be honest, it will not be solved only by the CTC, the Center for Transformation of Chemistry. This will be a global effort. We focus on 5 different areas: automation, standardization, data-driven chemistry, recycling, renewable feedstock, but also societal, environmental, and economic metrics. And the other thing is we are building a completely new entity in Germany. We have Max Planck, we have universities, we have Fraunhofer, and this entity, our KPI, our key performance indicator, is creation of jobs in this area. This was the largest chemical industry in East Germany. 92,000 people used to work in this area. It went from 92,000 to 12,000. Now it's at 43,000 again, but with the energy prices rising in Europe, there's a serious problem, and our goal is trying to actually change this. So we have a institute that's between universities and industry with our own venture capital fund and our own science academy. We organize the institute totally different, not like in departments, how we usually do it here and how we do it in Germany. We organize in 2 moonshots. And one moonshot is, and you might imagine this coming from me, we would like to replace humans from doing chemistry. Why do we have to do that? If Germany wants to stay competitive, for example, against India, we have absolutely no chance. Because the labor cost in Germany, no chance against India, China, whatever other country. We can't do it. So our only chance is if we actually start to be more automated. So what I showed you at the beginning was sort of a first step in my little world, but we'd like to take this to entire chemical enterprise. The second moonshot may be actually crazier, but I think that's what moonshots are all about. We would like to build a completely recyclable car. This idea came up in a discussion I had with the head of a board of BMW. And he said in 2040, we'd like to do that. If you really think about this, this is completely crazy. Because we could have also taken a bicycle or whatever else it may be, but a car, if you think about it, lots of strategic elements in the batteries, lubricants, adhesives, materials, paints, sealants. It's so much that goes into a car. It's all chemistry. And if you make all that circular, we'll have to work on all these things. And this is why we took it as a moonshot and say, okay, maybe we can start from here. I think while we do that, we will create new discovery pipelines. We will describe new processes and materials, just like people flying to the moon. We'll discover many things. And in Germany, that is the first time that we built actually a large center for chemistry. So far, we have medical centers, cancer center, biology, and physics, but never in chemistry. And so I think what's key for us is chemicals is the third largest German industrial sector of about 500,000 employees. 97% of all products used in Germany are made chemically or treated chemically, so basically everything you use. There's a huge dependence on fossil-free energy, resource-intensive, environmentally harmful, and frequent relocation, primarily here to Asia, China, India. And I think in the future we will have a circular economy, new business models, completely new chemical supplies. I am completely convinced that this transformation of chemistry will happen. The question, does it happen now and will it be driven by Germany, or will it happen in 10 or 15 years and driven by China? And if that's the case, then good luck with everybody, because that will totally change the ballgame. So we believe this needs to be done. We want to be the catalyst for doing this, and actually we have teamed up now with many top institutions, Oxford, MIT, Osaka University, other places, and we're happy to talk also to people in India about this, because I think this is a task for all chemists. I think that's where we need to go to. I can only give a start. I won't be seeing the end of this anymore. I think that's for young guys that are taken. I think they're excited to go there. Just to give you some sense, when we started this, we had 120 companies involved. Some of them you may imagine, BASF, the usual suspects up here. Interesting maybe the large forestry companies, because using starting materials from trees. Maybe you wouldn't expect a place like BMW or Microsoft. They are big supporters of all that because the data sciences. And as I said, we have now many other places combined with us. This was last year at Christmas. Every employee gets a BMW. No, I'm just kidding. Actually, the BMW factory is about 20 miles away from our institute. And so we actually looked at the automated assembly platform, because they can make cars automatically. We should also be able to do chemistry automatically. So we had our little meeting there. And that's part of the team. We are growing. We're at 45 people right now. 2 years ago this time, we had 3 people. Now we have 45. And of course, I'm really thankful to the people that did most of my academic work. What you see here, my department is about 100 people, but this is the group of people that work directly with me. You may have gotten the impression that only Indian students work with me. That is actually not correct. I just showed that just so you know that we have many, many good graduates from here. I'll try to see right here. Kapila Pradhan, she received her PhD. Professor Kulkarni here. She will come back to Mumbai actually in April, I think, to start an industrial career. I had to take an older picture of Rajat, who I mentioned in here. But just to give you some sense, Vietnam, Italy, Taiwan, Sweden, Japan, Vietnam, Taiwan, Czech Republic, India, Germany, Czech Republic, Cuba, Colombia, Venezuela, Serbia, US, Brazil, Italian, German. So that is basically what we do. Very international, all English speaking. We want the best people. We are lucky to get really, really good people. And typically, they do a good job with us. They do a good job with us. They have a great career, and that's what we want. And for me, it's really there to thank, A, the German taxpayers who pay for all the things we do around here, to thank my colleagues because they do all the hard work. I just sit in my office and travel and talk about stuff. And lastly, I'd like to thank the organizers for giving me the opportunity to give this prestigious lecture. I really, really appreciate that. I'd like to thank everyone in the audience. It's Saturday afternoon. I talked for a long time. I apologize for that. I hope it was worth it. Thank you very much.
Sorry.
Actually, I think it's such a fantastic talk that we are like spellbound. But, I wanted to go back to all the epitopes that you were using for development. Uh, how do you decide which of the carbohydrates? You know, there are so many. If you look at, for example, even the capsule, I'm just saying because I'm with AMR, this is my target, and not, you know, there's like a layer of LPS around it. And also, I wanted to know, when you have a carrier protein, is there a choice of a carrier protein which will have best immune response, and how do you decide that? I'm asking.
Extremely good questions, okay? I think the first question is really difficult to answer. We don't know this to this day, so what we do is we have some idea about uniqueness. So around the unique structures, we make libraries of compounds, each separate entity. That's why automated synthesis is helpful, because we can make a lot of them, and then we have to screen what works in humans and what doesn't. So basically, we look at the immune response of patients that recovered versus other patients, and then we started seeing antibodies against certain structures which correlate with recovery afterwards, and others not. And so then we focus on the ones that look good in humans. Actually, what we do now is we go with single cell sequencing. The idea is to go into actually recovered patients' blood and trying to pull the antibodies out. But it's not quite finished, that's why I can't talk about it yet. But I think that's where we're gonna go, because the discovery process that's the longest part. I didn't talk about this because it's not glorious. Students oftentimes make 50, 60, 70 compounds. We're lucky because we can do it faster, but that's a limitation. The second question you ask is an extremely good question. Let me see if I can. Okay. I think you asked about the carrier protein, basically. And yeah, so basically the question is, what are you going to use up here? The problem with a carrier protein is the cost of vaccine. Half the cost of vaccine is the cost of goods, and the other half is having to keep it cold. In Germany, not a problem. In India, more problem, okay? What we use typically is CRIM 197, that's because that's used. But right now, we have a huge program going for synthetic carriers. So we have, unfortunately, I can't disclose those because they're actually commercially very interesting. But we have now things which are no longer proteins or peptides, which are small molecules. And the issue there is, it's super interesting, but the moment you go to development, then it becomes a question. If you go into an area where CRIM has been used in everybody, basically, right? So the regulatory authorities are totally relaxed. So that's why Vaxilon, my company in this area, they went with CRIM because it's much easier to get in the clinic. Medium and long term, I think it's much better to go to other carriers that are fully synthetic, because you won't need a cold chain anymore. And that's what we're working on right now, where we really take different entities to go after specific subsets of immune cells. And I think that's where it's going to be attractive.
But the carrier protein has to be big enough to give you an immune response, right?
No, it doesn't have to be. No, there are other things. I mean, we published, for example, in Nature Chemical Biology in 2014, a paper where we showed that alpha-galactose, a glycolipid, stimulates iNKT cells, which are a relatively small population, but there are other things that do similar aspects. And I think that is where we want to go. So we want to go completely away from the proteins. We haven't published on that, but we've worked on it 6, 7 years now. I think that's where it could be interesting. Because what I really want is, I want a vaccine that you can leave outside at 40 degrees, you take it and you don't have to inject it, but you could do it either oral or nasal delivery, because that is really what we would want. We're not there yet, but I think that's where I would love to go in the future.
Thank you.
Peter, that was a great talk. The spectrum of topics you covered is fascinating. Because we are simple nucleoside chemists, we are dealing with the 4 building blocks and the coupling times and phosphoramidite chemistry. I'm just wondering, what's the coupling efficiency you have to deal with in carbohydrates? And how many building blocks you need to make? And that seems to be, quite countless. So can you comment on those?
Yeah. Let me start with the second question first. In 2007, we did a bioinformatics analysis of all the carbohydrate literature. It was known at the time for databases, and it's not great, okay? At that time, the surprising thing is that in mammalian systems, nature did not make everything that's possible, luckily. So actually, about 45 building blocks should suffice to make 90% of what's known. Of course, now I can argue maybe it's not all known, maybe much more, right? So, but I would say somewhere a bit 40 plus for mammalian structures. For bacterial structures, much more complicated, because bacteria really make many more things. Interesting for bacteria, but if you go in certain areas, certain families, but again, it's relatively few disaccharides that are combining. So with relatively few building blocks, can you make it? I would say if you look at the entire glycome, we're looking at hundreds of building blocks. And I think rightfully so, that is one of the limitations. However, I think if you provide access to 60, 70, 80 building blocks, that will cover most of the glycome as we know it. Second question, efficiency. So what we do is we call so-called, what we call approved building blocks. An approved building block is one I can make at some reasonable, at least let's say 100 to 500 gram scale, that are stable, and they're gonna give me a glycosylation above 90%. The glycosylations we get on a synthesizer today are typically 100%. However, when you go to complex structure, like some of the ones I showed you, these really branched ones, it's not so much a donor that's a problem, it's the acceptor. Because some of these carbohydrates likely also fold, like in peptide chemistry, like in G quadruplex, right, in DNA, that used to be a problem. Same thing here. So we are starting to learn now what may fold, what may become a problem. It's one of the reasons what I showed in the very beginning, where we're trying to actually interrogate many different structures. Of course, we only do monosaccharides. If you really want to do it, you should go to longer structures and then do the same thing again. So I think this is something we can predict. Today we are trying to use, again, machine learning approaches, trying to take what's known from the literature, feed it in so we can actually identify the areas where it's problematic. But it's going to take longer than for DNA, and peptides, maybe even to this day, you can't predict everything. So carbohydrates is going to be more like peptides and less like nucleic acids, from my perspective.
Thank you, Peter.
Hello. I don't have a question, but I just missed on something you were telling about gingivitis. Can you just throw light on it?
So P. gingivalis is one of the bugs that causes periodontitis. And periodontitis is approximately 7% of the global population. And it's not really related to poor dental hygiene. So if you have poor dental hygiene, there's chances bigger, but you can have really good dental hygiene and still there can be serious issues. What is known from anecdotal evidence is that people with this infection make antibodies against them, and these antibodies can correlate with atherosclerosis, with rheumatoid arthritis, and with Alzheimer's disease. And what we did is basically we made the carbohydrates, we looked at the serum and the saliva of these patients that have this periodontitis, and what we find were the antibodies, and then we started to look at the different body fluids of people with atherosclerosis, Alzheimer, and rheumatoid arthritis, and we're starting to see correlations. And that is probably that people get this disease, they make antibodies, and those antibodies create problems afterwards. But it's not just there. If you look, for example, at Epstein-Barr virus, very, very common amongst teenagers, right? Very common. There's also, in some cases, correlation with multiple sclerosis, and afterwards, also with cancer even. So I think it's not so totally surprising. The idea would, however, be if you could prevent those kinds of diseases happening in people, we could prevent the production of antibodies, and that then in turn may lead to these non-communicable diseases from hurting people afterwards. That's the approach to that.
Thank you.
I just have two quick questions, Peter. In your first part, we talked about the glycosyl part, right? So initially, when you had introduced this several years ago, at that time, community thought that it will only work for simple sugars such as mannose. In last 10 years, you have shown almost it works on several sugars. Are there any particular sugars which are not amenable to this glycosyl?
So I think on the glycosyl where we have issues or challenges would be the same ones you have in regular beta mannosides. They don't work really well otherwise. What we do is we take a disaccharide, pre-install it, and then put it in. That's how Joseph made the glycans. And the second thing is sialic acid. PhD student is finishing up right now from Taiwan in the company actually. He made sialic acid donors using the donors that are developed in Japan. They work on the automation as well, but they don't work as well as we would love to do, right? But if you do sialic acid today, it's always challenging. So I think what we see by automation is very much what you see also in solution phase chemistry. The only advantage of the synthesizer is we can actually add more building block, right, to push the reaction to completion, like in DNA. But otherwise, I would say the chemistry that works in solution is almost identical to what we see on salt support.
And last question related to what Ruchi asked, that we have this choice of diphtheria, tetanus, and CRM197. What about the antibodies generated by the proteins? Is that a problem?
I think that's going to become more and more a problem because as more people are going to get conjugate vaccines, if you're seeing the same, let's say Prevnar, right? I mean, more and more antigens. So your body is going to recognize CRIM or DT or TT more and more. So I think what has to happen next is going to be where we combine proteins from a particular bug with a carbohydrate from that bug, because then you have a double whammy, right? You have both a protein. I think by the end of the day, intellectually, we all know that needs to be done. The problem is if you go away from what's already done, the regulatory path becomes much more difficult, because you go to a regulatory agency and we have done that, and they say, oh, fantastic idea, Peter, please do this and this and this and this toxicology study and all these animal studies, and then you got to do like 10 years of studies before even going to clinic, right? And then people say, oh, the stuff's been in there, we make a small deviation, and then we get to a clinic faster. I think that's what's really pushing us. Intellectually, there's absolutely no sense to do that. It would be much more sensible to do this immediately. Right now, it's purely a development cost factor.
Okay. Thanks. One last question.
Hello, sir. Sir, have you screened any deuterionic polysaccharides for deuterionic polysaccharides?
Oh, deuterated polysaccharide. No, we did not. Actually, one of my postdocs in Japan right now is starting to put labels into compounds, but we have not published anything like that. But I think that is something that can be done today, because you put carbon labels in there, probably easier than deuterated, right? I think that is what we like to do, right? Give you access to these kinds of things, try them out on these synthesizers. So a good idea. Haven't done it yet for deuterated.
So if there are no more questions, please join me in thanking Peter for his fantastic lecture. Thank you, Peter.
Thank you, Professor. Thank you, Professor, for this enlightening lecture. As a token of appreciation, I would like to invite Dr. Lakshmi Ravi Shankar, an alumnus from GKT Group, to present a memento to Professor Seeberger. I would now request Professor Nandita Madhavan to come forward and deliver the vote of thanks.
So thank you, Professor Seeberger, for really spectacular lecture. It's very inspiring for the students as well as us to explore beyond our comfort zones, and you have conquered it all as well. So thank you for accepting our invitation and coming. I'd also like to thank the alumni from the GKT group as well as the Dean ACR office for the MOU and having this lecture. And of course, Professor GKT, without whose mentorship and inspiration, I think this wouldn't have happened. I'd also like to thank the head of the chemistry department and Professor Kaliyappan and Santosh for the invitation and all the arrangements for facilitating this lecture. And nothing is possible without support from our office staff. I would like to thank Shweta for all the work she has done along with her team. And I'd also like to thank Ratish for helping with the banners and the setup. I'd also like to thank all the other office staff who are involved with this, the CD team for covering this live and streaming it. And if I've forgotten somebody, please forgive me. Last but not the least, I'd like to thank all of you for being here. Over to, and Ratika for the great comparing.
Thank you. Finally, I invite you all to join us for high tea, which is being served outside, and we can proceed from the back door. Thank you.